3. So we'll begin with our quick look at the calendar. Today we're talking about the derivative at a point. And again, our first quiz is coming up on September 19th, which is a week from Friday. Okay? A week from Friday is our first quiz. So derivative at a point on page 23 here. Okay, so we need a reader for the daily summary. Can we start with Levi? Thank you. Cameron, 1.
For a general function, average velocity equals average rate of change, velocity.
Okay, so we've got our definition here for the instantaneous rate of change of some function at some particular x value, but it's the t value in this definition, is given by this crazy looking limit. But we've seen a lot of this stuff before. Remember, h was just some little tiny horizontal distance to the right or to the left. And so we've got these 2 points at a plus h and a, and we subtract the y values at each of those points, and then we divide by, subtract the x values at those points. And when you do a change in y over change in x, what are you finding? That's a slope. So this thing right here is the slope of the line connecting these 2 points on our curve. And then that takes the line that connects 2 points and really just makes it a line that's just barely touching the curve at 1 point. Tangent line is what we called it. So complicated looking definition, but we've seen all those pieces before. And the only thing that's new for today is that we're not only looking at like height functions or distance functions, but we're looking at any old function. And so down here in number 2, we're going to talk about this problem related to the population of China. So we've got our function p of t. It's the population of China, and it is roughly 1.267 times 1.007 to the t, where t is the number of years since the start of the year 2000. We're going to talk about these soon enough, but what kind of a function is that? What is it? Exponential function, right? Because the variable is up there in the exponent. So we'll review exponential functions later, but there's our first exponential function for this semester. Is this an exponential growth or an exponential decay function? Growth. How can we tell? That number right there is more than 1. Definitely going to be growing. Good. What does the 1.267 represent? It's the initial or the first population, right? So we start with 1.267, where's our unit? Billions of people initially, meaning back in 2000. And then it's just going to grow a little bit every year, and that function tells us how it grows. So here's what we're interested in. We're going to estimate how fast the population was growing at the start of 2013. That is all. How fast was the population growing at the start of 2013? So, for example, the population might be growing by 10 people per year, or 1,000 people per year, or 1 million people per year, but it's growing by some amount, and that's what we're going to find right here. Okay, so I guess the only calculus word in here is fast, which is to cue us in that we're doing this rate of change idea. So we're going to use that formula right there. I'm going to make one small change here. I'm going to change the p's to f's just so it looks more like the notation that we've got right up above. So just changing the p's to f's, but it's still our population function. Okay. A is the particular input value that we're interested in. What is the input value this question is asking about? It's 13, because we're trying to figure out what's happening at 2013. So A is equal to 13 in our problem. And so let's go ahead and write down our definition here. So it's a limit as h approaches 0 of f of, so all I'm going to do is change the a's to 13s. So 13 plus some little h minus f of 13 divided by h. So far so good. Just change the h's to 13, the a's to 13s. Okay, still copying that limit. We're going to use good notation here. And now we're going to use the definition of our function. Let's do the second part first. F of 13, there's my function. Don't give me a number, but give me something that I could type into the calculator. If I want f of 13, what do I want? Everybody agree? All we're doing is plugging the 13 for the t. We can highlight some stuff here for you. So that is this part. But we still need to find this f of 13 plus h. So we're going to put that right in here. And so it's the same idea, but instead of replacing the t with just plain 13, we're replacing the t with 13 plus h. So we're copying that whole function, but the t becomes 13 plus h. 1.267, 1.007 to the 13 plus h. Questions on that? Okay, and then the whole thing is still divided by what? H. Okay, so here's the tricky part, is that if every time we see a new limit, what should we try first? Just plug in. So when we let h equal 0, what happens on the top? And that becomes 0. We see that they cancel and it's just 0 up on the top. And what do we get on the bottom? Also 0. And that 0 over 0 is this dreaded indeterminate form, it's called, and it means there's work to do. It means plugging in just didn't get us an answer. Now, the work involved here, so we saw some of the work involved last class. Sometimes you can factor the thing. Sometimes if there's a radical, you could rationalize the thing. We're not going to do the work here. We're just going to approximate. This h going to 0 really means h is close to 0, but maybe not exactly 0. So how about we just pick a number close to 0 and use that? So let's use h equals 0.001, something really close to 0. It's not going to give us the exact answer, but it's going to be pretty close to the right answer. And so then all I'm going to do is copy my fraction, 1.267, 1.007 to the 13 plus 0.001. See, just change the h's to 0.001s. What do we put in the bottom? 0.001. That's it. And that's just a big old calculation, right? It's all numbers. So we'll use our calculator, we'll do the arithmetic, and we'll have our answer. So typing it in isn't going to be the hard part, but the setup was the hard part. Any questions about that setup? Okay, so it takes a little bit of time to type it in. Just have to be careful that you put extra parentheses around the top. And if I've typed it in correctly, then okay, I think that's right. So I'm just going to copy this down over here. This is about equal to 0.009677. That's enough. Okay, as soon as we get some units up here, this number will have meaning to us. The numbers on the top, this 1.267, and that stuff to the 13, what were the units for that calculation? It was billions of people, right? The F calculations on top were both billions of people. So this must be on the top of my fraction, billions of people. over. Now the h, we didn't, I mean, it was just h, and it seems like it's unitless, but it has units. So really what belonged on the bottom was 13 plus h minus 13, right? Remember we had that pattern? We would just copy the, oops, it's 13. We just copy the stuff on top without the function. And so really the units on the bottom are the units for 13, and the units for 13 plus h. What were the units for 13? Years. So that's what goes downstairs. So the answer to this problem is 0.009 and change billions of people per year. The last little twist, it says give your answer in millions of people per year. So what do I do with this thing? Yeah, times 1,000. So this is 9.677 millions of people per year. Questions on that? Okay, so there's one follow-up, which we're not going to write very much down. I just want to get it done quickly. But there was this other part that said also give us the answer, not just for 2013, but for the year 2000. How was the population growing back in 2000? And then we can have two numbers to compare. So I think everything is the same except what? Inside of this big long expression, what changes? These 13s both become zeros because 2000 was the year 0. So this is a really nice technique or trick on your calculator. If you do second enter, it will retype everything, and then you can just edit as opposed to starting from scratch. So what did we say? So the 13s just become zeros. So I think that's it. 0.008. So how many millions of people per year? About 8.8 millions of people per year. So that was the answer back in 2000. Just take a screenshot of that and bring it in case you look at these notes later. So here. Okay. And so now we have two numbers we can compare. This was the 2000 population. This was the 2013. When was it growing faster? In 2013, right? By almost 1 million people per year more. Okay, any questions on any of that? All right. Number 3 gives us a definition. Let's go over to Isaac. Can you read 3, please? Yeah, so that little apostrophe is just our notation for this new thing, this new calculation. It's called the derivative, and we read that apostrophe as a prime. So the most important definition of the entire semester, you are looking at it right now. It's that f prime of a, this new thing for the derivative, which is the instantaneous rate of change, is that limit. The derivative is instantaneous rate of change. A little bit of vocabulary in number 4, Ryan. Thank you. Brendan, 5. Okay, so we talked about this earlier today in last class. Secant line becomes tangent line. So we'll take a quick look at a sketchpad demo just to make to give us a visual of what's going on here. Okay, here is some random old function. It happens to be pi x squared. That's the curve there. And then we've got this special point that is sitting right here at x equals about 2. And then we've got this lemming. Now, lemmings just follow the leader, right? You guys know about those animals. So we're just going to let this lemming follow, get really, really close to the special point. So push the button. And that secant line eventually becomes tangent line. And the slope of that tangent line, I've just asked this program to calculate it, is 12.6. So in the new notation that we're seeing today, the derivative of this function at x equals 2 is about 12.6. Derivative just means slope of the tangent line. Brendan.
Now, to get the tangent line, where does you actually end up at the same point, or just get small?
Good question. So it depends on the question that we're being asked. If it says estimate, then we're going to pick a secant line that's like 0.001 apart from being a tangent line. But it might also say find the exact value, in which case we'll have to somehow do some algebra to calculate that limit. So we won't actually put in like 0.001. We'll have to do algebra like rationalizing if there's a radical or factoring if we can. So it depends on the question. And so, for example, if I take this special point and I move it up here, what would you guys think about the slope of the tangent line? It's not there yet, but is that slope of the tangent line up at this point going to be more or less than it was back here? More, because that tangent line is going to be steeper, right? So I forget what the number was down here. Was it 12 and something, 12 and change? All right, so the slope over there is about 44. That's the slope of that tangent line. That's the derivative at that tangent line. So every point has a slope. What could you guys say about maybe the slope of the tangent line here? What kind of a slope is it going to be? Negative, right? It's going to be going down this way. So we can move, and we'll get some negative number when the secant line eventually becomes the tangent line. So about negative 37 and change there, right? All right, so number 7 says the next statement is super important. The derivative of a function at a point is the slope of the tangent line of the function at that point. All right, so we're going to do some like chanting here. So who's our next reader? Is it Kyle? All right, so Kyle's going to read the stuff that's on the left, and we are all going to chant along with the stuff that's in bold. Go ahead, Kyle. The derivative is the slope of the tangent line. Kyle. The derivative is the slope of the tangent line. The derivative is the slope of the tangent line. Fantastic. All right, group activities start right there. I will help if I can.